All right. So this paper is joined with my frequent co-author, Andy Zapechilnyuk. And we're trying to understand connection between persuasion and delegation. So consider a principal who wants to influence the decision of a biased agent. And in this paper, we're going to focus on two common instruments of influence: delegation and persuasion. In a delegation problem, the principal designs a decision rule. And the delegation problem has been used to study the design of organizational decision processes, monopoly regulation policies, and international trade agreements. In a persuasion problem, the principal instead designs an information disclosure rule. And the persuasion problem has been used to study the design of school grading policies, internet advertising strategies, and forensic tests. Theoretically, in the delegation problem, the agent privately knows the state, and the principal commits to a set of decisions from which the agent chooses. Whereas in the persuasion problem, the principal designs the agent's information structure, and the agent freely chooses a decision. So in the delegation problem, the agent has full information, but the principal can restrict the agent's discretion. Whereas in the persuasion problem, the agent has full discretion, but the principal can restrict the agent's information. What are the trade-offs in these two problems? The principal's trade-off in the delegation problem is that giving more discretion to the agent allows for better use of information about the state, but it limits control over the decision of the agent who is biased. The trade-off in the persuasion problem is similar. Disclosing more information to the agent allows for a better use of information again, but it limits control over the decision of the agent. So these trade-offs are very similar. Moreover, the delegation and persuasion problems are two prominent instances of design problems without transfers in economics. In the delegation problem, the principal designs a decision rule that maps agents' messages about the state to decisions, but in the persuasion problem, the principal designs a disclosure rule that maps the states of the world into messages sent to the agent. And in this paper, we want to understand if there is a fundamental relation between these two problems. And the main result of the paper is that the delegation and persuasion problems are strategically equivalent. And this is established under fairly general assumptions. Specifically, for each delegation problem, we explicitly construct an equivalent persuasion problem, and vice versa. This construction, roughly speaking, equates the marginal utilities in the two problems and swaps the roles of decision and the states. Intuitively, in the delegation problem, the principal controls decisions, whereas in the persuasion problem, the principal controls the states, so information about the states. So there is a relation between the decisions in the delegation problem and the states in the persuasion problem. There are different kinds of equivalences, and the equivalence that we establish is a duality kind of equivalence. So why is this result interesting or useful? The implication of this result is that we can use the existing results in one problem to solve the other. How can we do this? Well, for a given delegation problem, our equivalence result immediately spits out an equivalent persuasion problem. So we can solve this equivalent persuasion problem using known techniques from the persuasion literature. And this solution to the equivalent persuasion problem is also going to be the solution to the original delegation problem by our equivalence result. One benefit of persuasion approach to the delegation problem is that the persuasion problem is a linear programming problem, and this problem is relatively tractable. Whereas the delegation problem is often not even a convex optimization problem. So dealing with delegation problems in general can be tricky. Now, the delegation literature has focused on what we call linear delegation, where the marginal pairs are linear in the decision. Whereas the persuasion literature has focused on what we call linear persuasion, where the marginal pairs are linear in the state. And we show that these are exactly the two equivalent classes of the delegation and persuasion problems. For this class of problems, we show that the main results in the delegation literature on optimality of interval delegation correspond to the results in the persuasion literature on optimality of interval disclosure. But the persuasion literature has gone a little bit further, maybe because the linear programs are a bit more tractable. So using tools from the persuasion literature, we extend and generalize many results in the delegation literature, and we also are able to solve novel delegation problems. And I will talk a little bit about them today. So this equivalence result also implies that the trade-offs and insights that arise in one problem have mirror images in the other problem. So equivalence result raises the value of doing research on either of the two problems. Because by doing progress on, say, the persuasion problem, you are automatically making progress also on the delegation problem. And we hope that our equivalence result will inspire people to study the relations in other variants of design problems without transfers in economics. Here we show a tight connection between information design problem, the persuasion problem, and the mechanism design problem, the delegation problem. And in a couple of ongoing projects with Alex Walitsky, we discovered a tight connection between information design problems and matching design problems, as well as gerrymandering problems. So many design problems in economics without transfers have a similar underlying mathematical structure. And we think that it's useful to understand this underlying mathematical structure. I will start with a description of the persuasion problem and the delegation problem. Then I will show you the equivalence result. I will discuss the application to monopoly regulation with a participation constraint, which will illustrate how the equivalence result can be used to address novel delegation problems. I will also discuss the application to discriminatory disclosure, which will hopefully shed a new light on the nature of our equivalence result. What I'm not going to do today is that I will not present the formal proof of the equivalence result, neither I will present the general results we obtained for the delegation problem, but this is all available in the paper. Also, to make the presentation lighter, I will focus on a relatively simple setting, but it can be generalized in many respects. So if you have questions about whether we can allow for this or we can allow for that, please feel free to ask me, and I may have an answer. So I'm going to start with what we call a problem. It will describe the common elements of the delegation and persuasion problems. And then I will branch out into the persuasion problem and the delegation problem. So in a problem, there is a principal and an agent. The agent makes a decision that lies in the unit interval, and the state is uniformly distributed on the unit interval. So here, of course, what I'm really assuming is that the set of decisions and states are intervals of the real line. The rest is just a normalization. We can always appropriately rescale the decision so that it lies in the unit interval, and we can measure the state in quantiles, and quantiles are always uniformly distributed. Let me now talk about the pairs and what we assume about the pairs. The agents and principals pairs depend on the state and the decision. We assume that the marginal pairs in the decision are well defined and continuous, both in the state and the decision. So this is just a technical assumption which we can substantially relax. Crucially, however, we assume that the marginal pairs of the agent is strictly increasing in the state and strictly decreasing in the decision. The first assumption So it seems that there are some messages. So did someone have a question? Okay, no one had a question. So the substantial assumption that we impose in the paper is that the marginal payoffs are strictly increasing in the state and strictly decreasing in the decision. So what that means is that the payoff of the agent is strictly supermodular in the decision and the state, and it's strictly concave in the decision. And we're gonna call the pair of payoff functions the primitive of the model. So this is all we need to know about the environment, given that we assumed that the state is uniformly distributed. And we will denote by calligraphic P the set of primitives that satisfy the above assumptions. Most importantly, this supermodularity and concavity assumption. So now I'm going to branch out and I will talk separately about the persuasion problem and the delegation problem. So I will start with the persuasion problem. We consider a monotone persuasion problem, which means that the principal chooses a monotone partitional information structure of the agent. So this monotone partitional structure means that each state is either revealed or it's pooled with some adjacent states. That is, the principal chooses a partition such that each partition element is either a singleton or an interval, where singletons represent the states that are disclosed, and intervals represent the states that are pooled into intervals. And because the distribution has a density, without loss of generality, we can assume that each pooling interval is an open interval, because it doesn't matter what we do with the boundary points of this interval. We can either reveal them or pool them, and it will not affect the expected pairs of the agent or the principal. So the monotone partition can be equivalently described by a set pi of singletons. So these are the states that are revealed. That is, we can describe a monotone partition by the set of boundary points of all partition elements. So to fix ideas, let me run through this example where the set pi consists of 2 points, 0 and 1/3, and also of the interval from 2/3 to 1. So the way we read this partition is that the states between 0 and 1/3 are pooled. The states between 1/3 and 2/3 are also pooled, but into another message. And the states between 2/3 and 1 are separate. And of course, it doesn't matter what we do with states 0 and 1/3 because they occur with 0 probability, but our convention is such that we actually reveal these states. So to summarize, the monotone partition is described by a closed subset of the unit intervals that contains elements 0 and 1. So this set is closed because we assume that all pooling intervals are open, and this set contains elements 0 and 1 because 0 and 1 are always boundary points of some partition elements. So pi is going to play a crucial role. So this is one piece of notation that I want you to remember. And then we denote by capital pi the set of all such pi's. So why are we looking at monotone persuasion problem? So first, we can argue that monotone persuasion incorporate constraints that are faced by information designers in practice. Monotone partition information structures are widespread, think about credit ratings, consumer ratings, and grade conversion schemes from 100-point system to ABC scale. And we think that monotone partitions are used in practice not because they are necessarily optimal among all possibly very complicated information structures, but because the designers are essentially constrained to choose monotone partitions. For example, when you choose a grading policy that gives better grades to some worse performing students, this grading policy will look funky and unfair, and it will also be manipulated by strategic students who can strategically underperform in order to get a better grade. So monotone partitions may be a consequence of incentive constraints in larger incentive problems, which we don't explicitly model here. But we also show that our equivalence result can be extended to include stochastic monotonicity rather than deterministic monotonicity. What that means is that we can allow signals such that the state results in a higher signal realization in the likelihood ratio order sense.
Anton?
And moreover,
can I?
Yes.
There is a question in the chat. I don't know if you see the chat. Otherwise, I can read the question for you.
Yeah, can you read it for me? Because
so the question is, can monotone information structure be shown as optimal in this game?
Yes, so that's a very good question. So I'm getting to this. So in general, persuasion problems, monotone information structures are actually suboptimal. But as I argued, in practice, it may be hard to choose non-monotone information structures. But in the particular instance of the persuasion problem that is particularly tractable and has been the focus of the persuasion literature, that is linear persuasion, where the pairs depend only on the expected state, monotone partitions are often optimal. And there are precise conditions under which monotone partitions are optimal. And in this case, we can, of course, drop the monotonicity condition in our equivalence result. All right. So, so let me get back to the monotone persuasion problem. So let mu pi of theta denote the partition element that contains the state. So we can interpret this partition element as a message that is sent to the agent when the state is equal to theta. Then after observing this message, the agent chooses a decision that maximizes his expected payoff given the belief induced by this agent. And the principal's problem is to choose a monotone partition that maximizes her expected payoff subject to the optimal behavior of the agent. All right, so let me now move on to the delegation problem. So we're gonna consider what we call balanced delegation problem, but let me first focus on the standard delegation problem, and then I will talk about the balance part. In the standard delegation problem, the principal chooses a subset of decisions, which is called the delegation set. Then the agent privately observes the state and chooses a decision from this delegation set in order to maximize his payoff. And the principal's problem is to choose a delegation set that maximizes the principal's expected payoff subject to the agent behaving optimally. So let me now talk about the balanced part of the delegation problem. Recall that the set pi, by definition, must contain elements 0 and 1. So that means that decisions 0 and 1 are always permitted by the principal. So how can we think about this balanced delegation problem, and how restrictive it is? So it turns out that we can often nest a standard delegation problem that doesn't have this boundary conditions that extreme decisions must always be allowed by doing the following. So we can define the payoffs of the principal and the agent on a sufficiently large interval of decisions, such that extreme decisions are actually suboptimal both for the principal and for the agent. So the agent never chooses these extreme decisions, and the principal shouldn't worry about these decisions. So this way, we can typically set up a standard delegation problem as a balanced delegation problem. And given this point, it turns out that balanced delegation is actually not a bug, but a feature, because using balanced delegation, we can address novel delegation problems with participation constraints. How? Well, so we can adjust one extreme decision, such as it's non-binding, and we can adjust the other extreme decision to represent the participation constraint. That is, the agent may always decide not to participate in the mechanism. And we will see how it's done in the application to monopoly regulation. So let me very briefly tell you about the results that shows how we can nest the standard delegation as balanced delegation. So suppose that the payoffs of the agent and the principal satisfy this and other type of conditions that says that the payoffs of the agent and the principal go to -infinity as decisions become infinitely large or infinitely small. And this kind of another conditions are typically satisfied in the delegation literature. In particular, they are satisfied when the payoffs are quadratic, which is the standard assumption in the delegation literature. So we show that there exists a sufficiently large interval of decisions such that the delegation problem is the same regardless of whether we choose a delegation set which is any subset of the real line or any subset of this large interval with the restrictions that the extreme decisions must be included. So intuitively, these extreme decisions are very bad for the principal and agent, so we shouldn't be worrying about including them in the first place, and therefore the balanced delegation problem and the standard delegation problem are actually exactly the same. So let me now illustrate the difference between persuasion and delegation. So in particular, I will illustrate that the revelation principle is not very useful for establishing the equivalence result. So let's start with the persuasion problem and suppose that the agent's payoff is this quadratic function here. That is, the agent wants to make a decision that matches the state. And let's us consider this monotone partition pi, which is represented by 3 points, 0, a third, and 1. So what that means is that we simply reveal whether the state is below 1/3 or above 1/3. And when the state is below 1/3, then the agent will choose decision 1/6, which is the midpoint between 0 and 1/3, given that the agent has a quadratic loss function and the state is uniformly distributed. And when the state is above 1/3, the agent will choose decision 2/3, which is the midpoint between 1/3 and 1. So let us now try to implement this decision outcome in the delegation problem, in which the agent has the same payoff function. So we're gonna look at the delegation set that contains only two decisions, 1/6 and 2/3. So if we include only these two decisions, then the agent will take decision 1/6 when the state is below 5/12, and the agent will take the decision 2/3 if the state is above 5/12, where 5/12 is the midpoint between 1/6 and 2/3. So we can see that this didn't work because the optimal decision, because the decision outcome differs on the set of intermediate states between 1/3 and 5/12. So that doesn't work. So what do we mean then by when we say that the persuasion and delegation problems are equivalent? So we're gonna do something slightly different. So instead of choosing a delegation set that contains decisions 1/6 and 2/3, we're gonna choose a delegation set that contains decisions 0, 1/3, and 1. So these are the boundary points of the partition elements. So if you do this, so if you include decisions 0, 1/3, and 1 in the delegation set, then the agent will choose decision 0 if the state is below 1/6. He will choose decision 1/3 if the state is between 1/6 and 2/3, and the agent will choose decision 1 if the state is above 2/3. So we can see that the decisions and states are now flipped. So the decisions are in red and they are at the top, and the states are in black and they're at the bottom. So in the persuasion problem, the states between 0 and 1/3 induce decision 1/6. And in the delegation problem, the type 1/6 is exactly indifferent between decisions 0 and 1/3. So essentially, the decision outcome in the persuasion problem is equal to the inverse of the decision outcome in the delegation problem. So there is inverse relationship between the decision outcomes in the two problems, and the roles of states and decisions are swapped. So let me now present the general equivalence result that we established. So we show that the monotone persuasion and delegation problems are equivalent, and now I need to unpack the definition of equivalence. So our definition of equivalence is sort of similar to strategic equivalence. We say that the primitives of the monotone persuasion problem and the balanced delegation problem are equivalent if the principal gets the same expected payoff in both problems. And this is true for each strategy pi. So consequently, since the payoffs are the same for each pi, the optimal pi is also going to be the same in two problems. Notice that pi is the same mathematical object in the two problems. It is the closed set that contains extreme points 0 and 1, but it has substantially different meanings in the two problems. In the persuasion problem, pi represents a monotone partition. More specifically, boundary points of partition elements. Whereas in the delegation problem, pi represents a delegation set, the set of decisions from which the agent can make a choice. And now I'm ready to present the main result of the paper. For each primitive of the delegation problem, an equivalent primitive of the monotone persuasion problem is given by these integrals. Conversely, for each primitive of the monotone persuasion problem, an equivalent primitive of the delegation problem is given by these two integrals. Okay. Note that if the primitive of the delegation problem satisfies the assumptions that we imposed, then the so constructed primitive of the persuasion problem will also satisfy the assumptions that we imposed. In particular, if UD is supermodular in the decision and the state, then so constructed UP will be strictly concave in the decision. And similarly, if UD is strictly concave, then so constructed UP will be strictly supermodular in the decision and the state. So why is this result useful? How can it be used? So suppose that you need to solve this delegation problem where the pairs are UD and VD. And you're not an expert in the delegation literature, but you know something about persuasion. So one way you can approach this problem is you can calculate these integrals and find the pair functions UP and VP, and then you can forget about the delegation problem and just look at this persuasion problem with primitives UP and VP. Then you can solve these persuasion problems using tools from the persuasion literature. So you find an optimal monotone partition, and then by the equivalence result, this solution is also going to be the solution to the original delegation problem, which means that you need to take the extreme points, the boundary points of the partition elements, and these boundary points of the partition elements will constitute the optimal delegation set. So this is how this result can be used. So let me now talk a little bit about these conditions that define the equivalence mapping between the persuasion and delegation problems. I actually find it easier to digest them when these integral conditions are restated in terms of derivatives. And here is how we can restate them. So this corollary says that primitives of the delegation persuasion problem are equivalent if they satisfy these differential conditions. And also, they need to satisfy these boundary conditions, but these boundary conditions are not very essential. So basically, they say that we normalize pairs in such a way that the agents and principals pairs from decision 0 is equal to 0, and in the persuasion problem, and the agents and principals pair from decision 1 is equal to 0 in the delegation problem. And of course, this is just normalization, which is with force of generality. So let me now focus on these two conditions. So you can see that they look exactly symmetric. One is written for the pair function of the agent, the first one, and the second one is written for the pair functions of the principal. So roughly speaking, we calculate the marginal pairs with respect to the decision in the both problems. And we equate these marginal pairs up to a minus sign. The important thing is that we switch the role of decisions and the states. How can we see this? Well, so in the delegation problem, the state is T and the decision is S. Whereas in the persuasion problem, the state is S and the decision is T. So I will not present the proof of this theorem or the corollary for that matter, but you already have a flavor of this result in the quadratic example. Essentially, what we do, we take a primitive of the delegation problem and the primitive of the persuasion problem given by the equivalence mapping. That is, the primitive satisfy these conditions. Then, for each strategy of the principal pi, we can calculate the agent's best response function, plug it in the principal's pair function, and calculate the principal's expected payoff. And then after some algebra, we can find that the principal's expected payoff is the same in the two problems, and this is true for each strategy pi. I will also highlight the economic intuition for the equivalence result in the application to discriminatory disclosure. So I want to take questions if anyone has some. All right, if there are no questions, let's continue. So the persuasion literature has focused on what we call linear persuasion. So this is a setting where the payoffs of the agent and the principal are linear in the state, or some transformation of the state, this function C of theta. The delegation literature, in contrast, focused on what we call linear delegation, where the marginal payoffs are linear in the decision or a transformation of the decision. And by our equivalence result, we can see that these two problems or these two classes of the persuasion and delegation problems are actually exactly the same. So the way to see this, so we need to take the marginal payoff in the persuasion problem, multiply it by -1, and swap the decisions and the states. So we will get this marginal payoff in the equivalent delegation problem, and this is exactly the linear delegation problem. So that means that the linear delegation and linear persuasion, which were independently studied in two strands of the literature, are actually about the same mathematical problem. And the results on optimality of interval delegation sets are actually exact same results as the optimality of interval disclosure rules in the persuasion. But the persuasion literature has gone a little bit further than delegation literature. In particular, the persuasion literature characterized when any candidate persuasion rule is optimal. So that will give us conditions that characterize when any given delegation set is optimal. So, so instead of showing...
Anton, can I ask you, before you move to the applications, so do you know of any other setting, aside from the linear setting, where the equivalence result, your equivalence results hold? Like, you know, as generally as in the linear setting? So, so if I give you a family of, so in other words, do you know of another family class of problems where your result can be directly applied without checking that that it actually holds?
Well, so the equivalence result holds very generally, as I alluded to.
But you need to check, right? So you need to.
So, well, so it holds very generally once you restrict attention to monotone persuasion problem. But without any monotonicity restriction, it holds pretty much only in the linear case.
I see. Okay, thanks.
But in any case, so linear case is the case where we can do the most progress. So it's sort of similar to quasi-linear mechanism design, so where most of the action was happening.
I see. Thanks.
All right. So instead of presenting general results, how we can extend and generalize the results in the delegation literature using tools from the persuasion literature, I'm going to consider an application. So this application will show how we can address a new delegation problem with a participation constraint. And it will also show how we can establish existing results in the delegation literature using tools from the persuasion literature. So So we're gonna consider a monopoly regulation problem. So here we're gonna have the monopolist who chooses the price or quantity in order to maximize his profit, and we have a regulator who wants to maximize social welfare rather than the profit of the monopolist. Suppose that the demand function is linear, so it's like here, and suppose also that the cost function is linear, where the marginal cost is a private information of the monopolist. And assume further that the marginal cost has a positive unimodal density. So this is a well-shaped, bell-shaped density function. The profit function of the monopolist is right here. So we take the difference between the price and the marginal cost and multiply it by the quantity demanded at this price. The regulator, however, also cares about consumers. So the regulator also has this triangle here. So this is consumer surplus. So originally this problem was studied as a mechanism design problem by Barron and Meyerson. But then people pointed out that in practice, transfers between the regulator and the monopolist are typically prohibited. And this problem then was formulated as a delegation problem, where the only thing that the regulator can do is to choose the set of available prices, pi. And then the monopolist can choose any price from this set in order to maximize his profit. For example, this set pi can take the form of a price cap, where the regulator imposes the maximum price that the monopolist can charge. So we're going to consider two versions of this problem. In the first version, we are going to ignore the monopolist participation constraint. So what that means is that the regulator can choose any set of prices, and the monopolist cannot exit. For example, the regulator can set the price to be equal to 0, and then the monopolist would be forced to produce 1 unit, even though he would have to sell it at price 0, which is below the marginal cost. So this is not a particularly realistic assumption in this application, but this is a standard delegation problem. So another version that we're going to consider is the version where the monopolist can exit. So this that means that the monopolist can always choose to produce quantity 0. And this is a novel delegation problem with a participation constraint. So let me start with this novel delegation problem because it's perhaps more interesting. So how can we represent this problem as a balanced delegation problem? Well, as I just said, the monopolist can always choose to produce 0 quantity. So that means that the monopolist can always choose to set the price equal to 1. So this is where the quantity demanded is equal to 0. That means that the regulator always allows price 1. Now, notice that selling at 0 price just doesn't make any sense, because 0 is below the marginal cost. So it's always more profitable for the monopolist to choose price 1 than price 0. That means that we can include price 0 in the delegation set without loss of generality, because this price will never be chosen anyways. And then if we define the state as quantile in this way, then we're going to have a balanced delegation problem. Okay? And since this delegation problem is linear, the equivalent persuasion problem is going to be linear as well. So what that means is that we can define the principal path in such a way that it depends on the message only through the expected state that this message generates. And if you do this algebra, which is pretty straightforward, you can show that the principal path as a function of the posterior mean state induced by a message is given by this function here, where the state is uniformly distributed on the unit interval. And this is a monotone persuasion problem. So to find an optimal delegation set in the original monopoly regulation problem, we can solve this persuasion problem, find an optimal information structure, and that will correspond to the optimal delegation set in the original delegation problem. So we can draw this function v of m. It turns out that it has this S shape because we assume that the density is unimodal. And when this pair function is S-shaped, then we know from the persuasion literature that it's optimal to separate states below some cutoff and pull states above this cutoff. And this cutoff is determined by the first order condition, which basically says that if we draw the tangency line through the midpoint of this interval, then it's going to be intersecting the pair function exactly at the boundary of this pooling interval. So that determines the optimal cutoff for this disclosure policy. Now we can reinterpret this disclosure policy in the delegation problem. So we found that this set is optimal in the persuasion problem. In the persuasion problem, this set is interpreted as upward censorship, where we censor the states above X star and we reveal the states below X star. In the delegation problem, this corresponds to a price cap, where we allow decisions below decision X star, below the price X star, and we also allow the monopolist to exit. So the monopolist can always choose price 1, which corresponds to exiting. So let me now talk about the monopoly regulation problem without participation constraint. So that will illustrate how we can typically nest the standard delegation problem as a balanced delegation problem. So to do this nesting, we're gonna extend the profit and wealth functions to the domain of prices between 0 and 2. So as we discussed, price 0 doesn't make a lot of sense because the monopolist will will have to produce at the price which is below the marginal cost, and price 2 also doesn't make a lot of sense. So these prices are never optimal; they're pretty extreme. So the optimal delegation set will not depend on whether these prices must be included or not. So that's how we can formulate the standard delegation problem as a balanced delegation problem. In this, so then we can apply our equivalence mapping and obtain the equivalent persuasion problem. In this equivalent persuasion problem, the principal payoff is going to be exactly the same function of the posterior mean state. But the difference here is that now the state is uniformly distributed between 0 and 2 rather than 0 and 1. So this function v is still S-shaped. So it takes exactly the same, so it's exactly the same as in the case where the participation constraint is present, except that now this function is linearly extended to the interval of states between 1 and 2. So since this function is as shaped, an optimal disclosure policy takes the same form. So we want to disclose states below X star and pull states above X star. But now this tangency line is going to be flatter. So that means that the optimal cutoff X star is going to be smaller. So there is going to be more pooling in the equivalent persuasion problem. And in the original monopoly regulation problem, that means that the price cap is going to be smaller. And this is intuitive. So when the participation constraint is present, the monopolist, the regulator is worried that the monopolist can exit. So the regulator gives optimally more discretion to the monopolist by increasing the price cap. Whereas if the monopolist doesn't worry that if the regulator doesn't worry that the monopolist can exit, then the regulator can give less discretion to the monopolist, and that is actually optimal. Questions about the application? So as we saw, so using persuasion tools, we can solve a standard delegation problem, and we can also solve novel delegation problems with the participation constraint. And this result for the novel delegation problem is completely new. So let me now move on to another application. So this application will shed a new light on the equivalence result. So you'll see how you can think about the equivalence result in a different context. So this application is called discriminatory disclosure. So now the agent chooses between two actions, 1 and 0. The agent has a private type. So this is new aspect of the problem. And there is still an unobservable state of the board. And we're going to assume that both the state and type are independently and uniformly distributed on the unit interval, on the unit square, actually. So to sum up, the difference is that here we have binary actions instead of continuous decisions, but now we have a continuous type. And another difference is going to be in what the principal can do in this problem. But let me first define the payoffs. We can normalize the payoffs to be 0 from action 0, and the payoffs from action 1 of the agent and the principal are given by these functions which are continuous in the state S and in the type T. You're going to assume that U, the payoff of the agent, is strictly increasing in the state and strictly decreasing in the type. So this corresponds to supermodularity and concavity assumptions that we imposed in the original problems. And economically, that means that the agent wants to take action 1 when the state is high and his type is small. Now, so what does the principal do in this problem? In the discriminatory disclosure problem, the principal chooses a closed set of cutoff tests, where a cutoff test Y reveals whether the state is above Y or below Y. The agent is going to privately observe his type T and then select a cutoff test from the menu of cutoff tests offered by the principal. And notice that we assuming that tests 0 and 1 are always allowed. So this is actually innocuous because test 0 simply tells you that the state is above 0, and test 1 simply tells you that the state is above 1, which is always the case. So these two tests are uninformative, so we may as well include them in the menu. Now, because of the monotonicity conditions that I imposed, without loss of generality, we can assume that the agent always follows the recommendation of the selected test. That is, the agent chooses action 1 if and only if the test says that the state is above y. So why is that? Well, so it never makes sense for the agent to flip and do the opposite because of the monotonicity. So it doesn't make sense for the agent to take action 1 when the state is below y and take action 0 when the state is above y. But one thing that that may make sense for the agent to do is to always take action 1. But this behavior can be replicated by choosing test 0, which says that the state is above 0 and then recommends to take action 1. And similarly, the agent can always choose action 0, but this behavior can be replicated by choosing test 1 and then following the recommendation of this test. So given this observation, we can formulate the discriminatory disclosure problem in the following way. The agent privately observes his type and then chooses a cutoff test from the menu of tests offered by the principal. And the agent chooses a cutoff test that maximizes his expected utility. Now the principal chooses a menu of cutoff tests that maximizes the principal's expected utility given that the agent behaves optimally. So we can already see that this discriminatory disclosure problem has a flavor of the delegation problem and has a flavor of the persuasion problem. Just as in the delegation problem, the agent here privately knows the state or his type T and chooses a decision, chooses a cutoff test. But just as in the persuasion problem, what the principal actually does here is he's choosing the information structure of the agent. And that sort of shows where this equivalence is coming from. So let me give you a bit more details about why this problem is equivalent both to delegation and persuasion. So to think about this problem as a balanced delegation problem, we need to think about agent of type T who chooses a cutoff test from the menu. And we're going to integrate the state out. That is, we're going to define the expected payoffs before the state is observed. And this is exactly the balanced delegation problem. Then to view this problem as a monotone persuasion problem, let's think about a menu of cutoff tests as a monotone partition. So if you observe all tests in the menu, then you will observe a monotone partition of the set of states. And then, so by looking at this induced monotone partition, we can ask what threshold type the agent would need to choose for choosing action one. So the agent observes a monotone, the agent observes a partition element that contains a true state S, and then chooses a threshold type Z, which means that the agent will choose action one if and only if the actual type is going to be below this threshold type Z. And here, the expected pairs are calculated before type T is realized. So we sort of integrated the type out, and here the state is S, and the decision is the threshold type. Whereas to view this problem as a delegation problem, we need to integrate the state out, and we should view the type as the state, and we should view the cutoff test as the decision.
Yeah, Anton, so
Yes.
can I ask you something?
Yes.
So when you say the expected expected payoffs, these are the agent's payoff. So
Well, these are the principal and agent's pairs.
I see. And so in one problem, they are calculated before knowing types. So the agent knows types, he doesn't know state. In the other one, the agent knows states, he doesn't know types.
Mm-hmm. Yeah, that's exactly right. Okay. So there are just two ways to look at the same problem.
Yeah.
So we can define the pairs before the state is learned.
Yeah.
And the agent knows his type, and his relevant decision is a cutoff test from the menu.
Yeah. Yeah.
So
yeah.
this is why it's a delegation problem. But to look at this problem from another perspective, we can look at the information generated by all the tests. So that defines the monotone partition. And then the relevant decision of the agent is to choose a threshold type.
Yeah.
And here the state is S, and the threshold type is the decision.
I see. So, and in a sense, regardless of which one you as the analyst choose, you can solve this. So you can solve the discriminatory problem, the discriminatory disclosure problem by analyzing it either as a monotone persuasion or as a balanced delegation. That's the point.
Exactly. This is exactly the punchline of this application.
Yeah. Cool.
And well, so this application also builds a bridge between the balanced delegation and monotone persuasion. So these three problems are actually equivalent. So you can solve one of them using tools from any of the other two. All right, so this is pretty much all I had for today. So let me now briefly tell you what else we do in the paper. So we establish the equivalence result under more general assumptions. So instead of assuming that the marginal pairs are strictly monotone in the decision and the state, we actually need to impose some weak single crossing conditions on the marginal pairs. So here I assume that the state was uniformly distributed, which in particular meant that there are not atoms. In the paper, we show how the equivalence result can be extended to settings with atomic distributions. And also, we can easily allow for discontinuous marginal pairs. Then, as I already told you, in the new version of the paper, which is not available yet, we extend the monotonicity conditions, the deterministic monotonicity conditions, to stochastic monotonicity conditions. So now, in the persuasion problem, the principal can choose not a monotone partition, but a signal that is ordered in the likelihood ratio order, such that higher signal realizations result in higher beliefs in the likelihood ratio order. And in a special instance of persuasion and delegation problems, in particular in the linear persuasion and delegation problems, we can drop the monotonicity altogether. So the equivalence holds generally without imposing any sort of monotonicity conditions. And then, so another thing that we do in the paper, we show how the tools from the persuasion literature can extend and generalize results in the delegation literature. So the delegation literature focused on characterizing conditions under which an interval delegation set is optimal. But now we can easily characterize conditions under which any candidate delegation set is optimal. So in particular, we can characterize conditions under which two interval delegation set is optimal. Moreover, at least in the linear case, we can also easily handle stochastic delegation sets. And we can show under which conditions a certain stochastic delegation set is optimal. And we can also show under what conditions a certain deterministic delegation set is optimal among all stochastic delegation sets. And all of this can be done with or without participation constraints. So to conclude, in this paper, we show that monotone persuasion and balanced delegation problems are equivalent. They are also equivalent to a discriminatory disclosure problem, where the agent is informed, but chooses between just two actions. And the implication of this equivalence result is that the insights and results in one problem can be used to understand and solve the other problem. In particular, we illustrated how you can do it by obtaining new results for the delegation literature using tools from the persuasion literature. But the analysis can be done in the reverse direction as well. So potentially, you can extend the results in the persuasion literature using some tools from the delegation literature. Thank you very much. And so we may have a few minutes for questions.
So we have, yeah, indeed. Thanks, Anton, for this wonderful presentation. We have a couple of minutes for questions. So if you want to ask questions, just unmute yourself and we can discuss. Okay, so Anton, you have been too good. You have left us speechless.
I'm not sure about that, but I'm very thankful for.
No, I think it's a wonderful talk. Actually, I think it's a wonderful paper, and I think it will be really, really useful for a lot of people working on this area. So let me then end the meeting and thank you, Anton, again, and hopefully we'll see you next week with Jonathan Lipgover. Okay, yeah, so stay tuned, and thanks again to everyone, and especially to Anton.
Thank you all.
Okay, bye-bye.